Okay, you are live.
Hello, everyone. Hi.
Hello.
Let's welcome everyone to our meetup. Hello, Rina.
Hello, Michael. Hello, and hello to everybody else. It looks like it's working, so I have YouTube opened and
great.
It's working.
So we are on air, right? Let's wait maybe a few more seconds until we have the official start at 5:30 here Central European time, and then we'll start the party. We have a reason to party today.
Exactly.
Great. Yeah,
hello
Rina, how
from
are
Brazil.
you?
Okay.
I guess there were some interesting changes. Hi. Yeah, I guess we have an international audience, quite some people that will likely join today. More than 100 and more than 150, I guess. Yeah. So will be a great time. So Rina, are you ready? Let's get the party started, right?
I'm ready. Yes, we can get started.
Great. So the reason why we meet today, Manfred told me back then, in the ancient times, let's call it that way, when Manfred was honored with a Google Developer Expert degree. One of the other Google Developer Experts, a good friend of us, Web Dave, he invited him to Meetup to actually celebrate that Google awarded him with the Google Developer Expert, and the same reason why we meet today, because my colleague next by, it's an honor to congratulate him to his Google Developer Expert degree. So great work, well deserved. Let's get the party started. Maybe some initial words from your side.
Right? Thank you, Michael. So I have to do a victory speech or something like this. So I can just say thank you, of course, to the community, because Google Expert is actually a title that you get for community contributions. And there were some people who made this actually working on an official side. That is more or less Santosh. He's not here today, but officially now, thank you to him as well. And of course to you, Michael, and also to Manfred for being actually my colleagues and challenge me all the time to always come up with the latest content and all that stuff. So very short victory speech. Nothing else to say except thank you. And I will not disappoint you. So I take this very serious, and I will continue to do this kind of community contributions that I've already done in the past, now in the future as well.
Yeah, perfectly well. I guess almost everyone here will likely know the engine news. So
hopefully.
Your format, your weekly format. Maybe let's explain a little bit for those who maybe don't know engine news.
Yes.
What's about that?
Yeah, so it is actually a weekly newsletter in the form of a video. That was the initial way how we did it. So it lasts 100 seconds because we all don't have so much time. So what I do on Saturday or on Sunday, but also during the week, I start collecting all the different things that happened in the community. And then I kind of try to summarize them, try to squeeze it into 100 seconds. Then I make a media recording, which takes very long because it's just very short. And after that, there is a post-production, and then it's obviously also published on different channels. And in the meantime, there is also a written version of it. I think not many people know of it, because the major number of the subscribers comes from Twitter. But on Dev2, on Medium.com, and also on LinkedIn, that one actually grew quite fast. There is the written form, and the written form always has a little bit more, because I always have to shorten the clip. I also have to drop out some of the content, but in the written version, you have all of it. Yeah, so if you wanna keep up to date with engine news, I would say if you wanna stay up to date with Angular, then I think engine news is a good choice. I hope so.
Super great. So to sum it up for the community, we have engine news. We have Enea, who is spoilering all the PRs so that we know what's going on. We have the Angular team that is actually implementing all that stuff. And if you like, continue to join our meetups. for some interesting topics. And basically, this gives me exactly the chance to hand over to Rina once again to start with the first session today.
Yes. Okay. Thank you very much. And again, hello to all of you. I try to share my screen. Let's see how this works. Okay, you see my slides.
Looks good, thanks.
Okay.
Yeah, fine. That's good. Fine.
Okay. Then, so welcome to my inaugural, or I don't even know how to pronounce it, but to my first official talk as GD, Signals Under the Hood. And well, the introduction slide, first of all. So my name is Rina Hahnekamp. I'm now also GD, and I'm also working for Angular Architects. Yeah, but let's come back to the content of the talk. So the idea of this talk is that you should get a real understanding about the way how the signals work in Angular, because I don't know how it was for you, but when I saw them the very first time, it almost looked like magic. So we had this kind of computed function where we just called the signals, just executed a function call, and almost from nowhere, there was an internal connection made. So the computed always knew that it had to rerun its internal computation function when the signal changed, and I didn't have to do anything. So I don't have to subscribe or something. And then we also said that in some other parts, for example, when we have so-called side effects, so it could happen that somebody adds a console log into the computed, that there are also maybe that there are some situations where the console logs didn't show up. Maybe not all of them, only parts of them. And this was also, or this could also not be very clear what this is all about. So what I did in preparation for this talk, I took a look at the source code. It's actually not that much because the Angular or the signals part of Angular is quite isolated from the rest of the framework. There is obviously an integration into it, but the core functionality, that one's really isolated. So you don't have to go over thousands lines of code. And what I did is that I tried to remove all the code which was more or less connected to the very advanced parts of the signals. And I really tried to reduce it to a more or less to a core part where I say, okay, this would be very important to understand how it works. And I ended up with 80 lines. And this is what I'm going to want to implement today, a kind of a very minimal prototype that gives you this kind of understanding of the signals. Yeah, and other than that, if you really want to know more, there is also something more in preparation. So in November, I plan to publish a video which also contains the advanced techniques. Also, maybe this is here the first part, that the first part comes a little bit in a more detailed version. So I will say this at the very end of the talk again. But if you're interested in that, you have two choices. You can first of all subscribe to my YouTube channel, or you subscribe, or maybe even end subscribe to our newsletter on Angular Architects.io. So Manfred will send it out once these two videos have been published. The way how the prototype will be implemented is by using test-driven development. So I have prepared 4 unit tests. We will do this incrementally, and we will start first of all with a little bit of a warm-up. Also warm-up for me, implement the signal function. Then we start with a very, very simple version of the computed. Then the reactive computed, which can already do a little bit more. And then we reach the actual computed, how it really works with the push-pull algorithm, and which is something which is then also required for the glitch-free effect. And by implementing it, I hope that you also get this understanding and then really can kind of understand in a way how the signal work, and also that you don't have any bad surprises when you use them in your applications. The advanced topics, I have actually no slides for them, for the effects a little bit, but I will just cover them in theory. So I will just say a few sentences about them, because as I said, in my opinion, they're really the core part of the signals, which is important for us as application developers, is covered in the first part. And at the end, we also have the quick Q&A if there are some questions. Good. So let's start. So this is already our first unit test that we have here. So we want to create a signal. So what we have here is a signal method. we want to place here an object literal into it. It's a typed object literal. In this case, it's a meal. It has a name, it has a price. And in that case, it's an Austrian dish, a typical Austrian dish, that's a schnitzel. And once I call signal, the return type is more or less a function. And whenever I call that function, it returns me the same value again. And then I also have here the option to update my signal. I have the set, and I also have the update method. And as you might know, the mutate method was also available, but it doesn't exist anymore. So in Angular 17, mutate has gone away. It will only be about set and update. Yeah, so this is what I want to implement now. So I go to my IntelliJ, right? I will first of all create a new file. So you see here, it's an empty project. There is nothing in there except vtest. So I say here signal spec yes. I say this is my first unit test. This is the test that you have already seen before in the slides. And then I start to create another file, which will be the implementation. So I say here signals ts. So window, let's split it up, I hope. So where can I never do that. So yeah, here it was split to the right. So somewhere the test should show up. On the left side, we have our test. On the right side, I will do the implementation. And I will make it very easy for me, because for now, for the first try, I will more or less comment out the set and the update. So the signal is actually just a function which returns a function. And this is what I'm going to do. So I say I have a generic function. It gets an initial value. And what that one is doing is that it just returns a function that is giving us back the same type, more or less. And since I want to return the same value again, I more or less, everything that I have to do is that I say, well, there is now a function where I say return initial value. This is it. So if I save it, and I'm going to import it here in my unit test, then we hope that this one is more or less working. And it works. Yeah, test results. I hope my keyboard stays alive. I just got the notification that the battery is running slow. But yeah, we will see. Good. So this was more or less, it was not that hard, I would say. Now it becomes a little bit more interesting, because now I say, okay, I want to have the set and the update method as well. See, the test is again failing. Wonderful. What can we do? The problem now is that I'm already returning a function, and this has to be a function now which comes up with further methods like set and update. How do I do that? I would say let's start first to come up with a real type. So I don't want to type the type here. I want to have a real type for it. And obviously, I'm going to call this type signal. So I say, yeah, this is a type which returns a function, and then I can replace it here as well. So, and since I have now a type, what I can also do is that I can make use of the intersection. So I can say here, it's a function. Yes, it will also stay a function returning a value, but it will also have something else. It will have, for example, a set method. This set method gets a new value of type t, and that one's going to return void. So the set method doesn't really do anything, so it doesn't return anything. And then we also have an update method. So let's say we have here update. This update method gets a parameter, which is an update function. And what this function gets is a value of type t. And we would expect that this function returns us another, more or less a value of the same type again. And that one also returns a void. And now we see already we have a problem in terms of TypeScript, because now TypeScript says, well, if you say you want to return a signal, then you have to make sure that these two methods are included as well. So I have to do a change here. So first of all, I would say, let's create a real function out of it. So let's call this function signal fn. And it will return now the initial signal, although we know actually that this initial value will not stay alive very long. We will also be able to change it. So I want to say here, okay, there is a value, and then I'm going to assign the initial value to it, and this function will always return the value. Good. And now, because of course I have to return the signal function there, and now I have the option to say signal function, and I just start adding my new methods to it. So I say, okay, there is now a set property getting the setter function. So I say, okay, you give me a new value of type t, and I'm going to assign the new value internally. And I'm doing then the same for the update function as well. So I say, okay, there is update. There is now the update function. That one gets the current type. And I would expect that it returns again the same type. And that means now that I say here value equals, I call the update function and provide the current value that I have. So I'm just adding functions to an existing function. This is something that I've done here. By, of course, also making sure that it's type safe by providing here an own type as well. And we see that the tests are already turning green. We can now try it out. So I could, for example, I just want to verify that my tests are running. So I will make here a breaking test. I say here it should be 9, although it should actually be 8. And we see now that the error message shows the right result or the expected result. So I can say, okay, I'm safe in terms of the tests. Yeah, so this was the first part. This is the signal function with the type and with the implementation, with a very easy implementation. Now let's continue with the next one. I said there are 4 exercises or 4 unit tests. The next one is now about a very simple computed function. So I say I still have my signal, the lunch signal. I now have a computed function, a new one. And what I'm doing in this computed function is that in this case, I'm returning a string which consumes this lunch signal. And it's like more or less a formatter function, as you can see here. It says schnitzel and the price that it has. And when I want, or when I actually going to update my signal, then I want when the next time, when I call the pretty name, that it gets the updated, or that it returns the updated value as well. So that's the goal. And the way how the implementation looks, I have prepared here something. This is so that we have here the 3 elements, more or less. We have here a caller. This is more or less, in our case, it's the test. There is also the term of reactive context, which let's forget about this now. And so somebody is calling the computed. The computed is then calling internally its computation function. It goes to the signal. The signal is more or less, or the computed requests the value from the signal. The signal returns the value to the computed. That one is doing some kind of processing and passes it on to the controller. This is what we do here. If the signal gets a new update and the caller comes along and says, I want to have now again a new value for it, so it's not reactive at the moment, the caller, then the signal returns the new value, the computer processes it, passes it on to the controller, to the caller, which then has the new value. So as we see here, very simple, the computer doesn't do anything in terms of caching or like keeping the value. It's always recomputing it. Good. So how can we implement that? I go back and I say, okay, I have now my second unit test with computed. So computed is a function. Again, it's the same code that you have seen before in the slide, so that's not something new. And I say here, export function computed. Again, a generic function. We say there should be a computation. And this is, again, a function which returns me some kind of type. I'm not interested in the signals that this function or that this computation internally calls. That's none of my concern. And what I want to return is then a signal of type T. Good. So how do we do it? Well, we would be able to get away very easily by, again, saying, okay, let me just call the computation once you're executed. I can save this actually. Of course, I also need to import now the computed. I can save it now, and we see now the test is already running. That's how simple it is in the first iteration. But we have already a problem coming from TypeScript, because TypeScript says, hey, that's not a signal what you're returning here. This is a function, but not a signal. By the way, the reason why the tests here are working is that vtest in the watch mode doesn't do anything in terms of type checking. It just executes the code right away, which is also one of the reasons why it is so performant. But yeah, either way, we have to fix it. And well, if you know the types in Angular, then you know that there is not just a signal type, but that there is also another type, which is the writable signal. So there is not really a read-only signal and a signal. It's more or less that the signal itself, the signal type, is that one that is more or less the read-only version. So I say here, I have a type signal, and then I also have a new type, which is a writable signal. And that one extends from the current signal. So it says here, yeah, I'm a read-only signal, if I'm allowed to say it like this. And then I'm applying here the intersection. And my computed, that one will return the signal. And the signal function itself, that one is the one which returns the writable signal. So we just had now to make sure that it also works in terms of the typings. If you look into the source code, you will also see that the signal is really a type and the writable signal is actually an interface. There are some reasons for that, but I didn't find really a comment why it was done like this. But yeah, this is normally the way how you would see it in the source code, if I'm not mistaken. Good. Well, second test already done, so it goes very fast. Now actually comes the long part. So now for the next one, I have to do a little bit more than just adding a few lines. That one is more or less the hardest part. So please, this is now the point in time where you should focus, and then it hopefully gets quite clear. So we stick to our computed, but we extend it now in terms of functionality. What I want to say, I want to write a test that verifies how often that function in the computed is executed, because there are some rules for that. First of all, I don't want that my computed function runs when nobody accesses it. So I say here, pretty name is defined here, computed count is increased all the time when it's executed. And I say by default, when nobody actually calls pretty name, then nothing should happen. The computed count should still be 0. Only if I say then pretty name, I'm not really interested here in the return value. I'm more interested how often the function runs. Then I say, okay, now this is more or less the trigger where the pretty name is more or less executed. And then this is now the interesting part. I say if I run it again and the underlying signals or the signal hasn't changed, then the computation function should also not run. It should really only run if I change the update or if I change the lunch here, and if I call them pretty name, then the computed count should be have a cycle or a runtime of 2. That's what I want to achieve. So I really want to. So in this case, I really need to know, or the computed need to know, first of all, about its kind of signals that it is using internally, and then of course it also needs to be notified by those signals. It's a little bit more challenging, as I said. And the way how we will approach this, I have here a second animation. And you see here that there is now something new. There is an active consumer, which is a global variable, which we still have to declare. And the signal, as you see here on the left side, it also has now a new property, which is a consumer's property. It's a consumer's array. So once the caller starts to request the value from the computed registers itself as an active consumer. Only then does the computed start with its computation function, and that means only then accesses the computed the signal. Now what the signal is doing, once it sees somebody wants to have the value from me, it checks if there is an active consumer set. And if that's the case, the signal fetches the active consumer, stores it internally, and then sends just the value back to the computed, which is then doing its stuff, and then provides or passes on the value to the caller. But now the signal is aware that there is a consumer in place. Because now next time, when the signal is changed, then the signal is automatically updating our computed. In this case, in this incrementation step, it sends the updated value to the computed, which is doing its stuff. And as you see here, the computed stores the value. So this is something what we also have to introduce. The computed needs to cache the value. Because if then the caller comes later along, the caller goes to the computed, it says, hey, I want to have the value, and the computed says, okay, it's right there. And that also means that now the caller can, as often as it wants, request the value from the computed. It's only doing the computation, the internal computation, once the signal is activating or notifying it. So in the end, you can also say the computed doesn't actually know about the so-called producers, which will change, which in the advanced topics will change. But for now, the computed completely relies that somewhere the producers are aware that it does exist. And in order to make this working, so in order, when we say here, well, we want to store the computed, so we want to store the element of the computed somehow, we need to come up now with a type which represents the computed, the signal, and we call this type the so-called reactive node. And this is what I have to start with. So when I want to store somewhere the active consumer, I need to come up with this particular type. So first of all, the test. Signal 3. We know already how it works. And then I say here, okay, where we have our types, I come up with the new one. That's an internal one. And I call that one, that's now the reactive node. Again, a generic type. And it has some values. First of all, it has a value itself. So again, the signal and also the computed can place their value into that property. For the producers, so from now on, I call those who need to update somebody else a producer. For the producers, we need to have a property for their consumers, so they need to store them. And that's again reactive node of type unknown, and it's an array. And for the consumers themselves, who are then being updated or notified by their producers, we have to have some kind of callback function. So the producer needs to find a way how to tell its consumers that there is a new value. And I make it very simple here. I say that's on value change, which in the end is just a function which returns void. So very simple. What I will also do is that I will create a factory function. So I will create myself a factory function that generates a reactive node. Maybe it's not necessary for these small things that we do here, but it will pay off because the code gets shorter in the signal in the computed then. What the reactive node requires is first of all a value of type t, more or less the initial value, and then optionally the factory function says, if you want, to the caller, if you want, you can provide me with values for consumers or also for the on value change. So in the end, that's a partial of a reactive node, which we would expect here. And since it's optional, we say, okay, if you don't pass me anything, then it's just an empty object, literal. But I will promise you that I will return you a reactive node of type t. Yeah. So we have some kind of default values. So we say here, okay, our default values are that our consumers are empty, and on value change is actually just a function which doesn't do anything. Let me make this a little bit more type safe. So I say here, this should be a type where I say I take the reactive node, but I don't really care about the value because that one is mandatory. And then I'm going to return, first of all, the value, an object literal containing the value. This is what I will receive. I will come up with my default values. And then if properties are there, if I want to override the default values, then they come at the end. And this is what I'm now going to return, so the reactive node. Good. Now we need to integrate the reactive node into the signal and into our computed function. So it's not the case anymore that there is a let value flying around. It's more or less like the signal now says, okay, I generate for myself this reactive node. So I say here, create reactive node. I will provide my initial value. And since the consumers array is already initialized, I don't have to care about anything else, except that I say I need to return now the value coming from the node. So here and here and here, and this is wrong. How does this, what's the shortcut for multi-selection? Yeah, like this. So we're returning the node. And then I have my computed, and the computed more or less has to do the same thing again. So here we have again our node, where we say I'm going to create a reactive node. Yeah, and now it starts to become a little bit interesting, because what do I want to provide now to my create reactive node? I don't want to start the computation, so I don't have an initial value. I want to start with the computation when somebody wants something from me. So when I'm being called. Now there are different approaches to the problem. We could say the value could also be undefined. So I would provide here an undefined. Unfortunately, what if we say the signal itself also has a value of undefined? Then I can't differentiate it anymore. So what we see in the original is that there is now a very special symbol, a unique value, which is called unset. So that's now here a symbol. And symbol means when I call symbol, the function symbol, it generates me a unique value where only I, because I'm not exporting it here, where only I have access to it. And I'm using now the unset as an information for the reactive node that it hasn't been initialized yet. So I say here unset. The problem now, of course, is TypeScript has now a problem. It says, hey, you can't provide me with an unset. This is a generic type T. This is not going to work. And in this case, we have to cheat a little bit. So I need to go to my create reactive node there. And what I have to do is that I have to say, okay, you can also, if you want, you can provide me with the type of unset, but I will still, so we will apply here type assertion. I will still return you the reactive node of type T so that it's really fully type safe. Good. Now we are happy in terms of computed. What the computed also needs to do is that it needs now to define this on value change, this callback that I have in my reactive node, because here it can say if my producer is telling me that there was a change, I just go to recalculate the value again. So I say here on node value equals computation. Computation. Like this. I don't care about the consumers. They are empty. And then we need to add further things, because now actually I want to come up more or less with a function so that it's more or less is like the signal. So I say this is here the compute_fn, and the compute_fn is returning me the node value. And at the end, I'm returning the compute_fn. So this was just a small refactoring. So it's a little bit similar to the signal. And now I need to include the probability of an unset, because, well, obviously, if I'm being called for the first time, I need to run the computation also for the first time. I need to set the value. So I say here, if the value, if that one is actually unset, then I want to say, okay, then please run also the computation, because now you are needed. Then I'm returning the value as I have done it before. Good. So now we have actually integrated, or this was more or less a preparation of what comes next. We now have for computed and for signal an own type, a reactive node. That one already has a callback. So what I can do now is that I now can come up with this kind of active consumer. So I can say at the very top again, I'm generating, or I'm creating here my new, where do we have it? Here, active consumer. It could be this a reactive node of type unknown, we don't know, or it could also be an undefined. So, and our computed now needs to register itself for its producers by setting itself as the active consumer. So I go to my computed and I say, once you run the computation, and here we make it very simple. We say, well, the producers are always the same. They don't really change. So I'm going to register myself only once in the very beginning. So I say here, active consumer, that's actually me. So me as from the perspective of the computed function. And it could be the case that there is already an active consumer set. And I have to take this into consideration. So what we usually do is that we say, okay, there is a previous consumer might be there. So I'm setting it to the active consumer. Then I run the computation. And when everything is done, I clear up and I'm reassigning the previous consumer back to the active consumer. So I leave the place as I found it. So I say here, active consumer equals previous consumer. In Angular, you will see that these two lines, there is actually a method for that. And that method is called consumer before computation. This is one. And then there is also another one, the afterwards, obviously, where we say computed consumer after computation. This is something you will also find in the source code. If you're curious, you will see that there are many smaller functions which, so it's actually, which you have many functions, but they are more or less short. This is the way how it is done. And you will always find the same names again. So I try to stick here to the original as much as possible. Good. So we are registering yourself as our active consumer. From the computed, we also have clarified that once we are being updated, notified by our producers that we are rerunning the computation. Let me quickly think if I haven't skipped here anything. I don't think so. We will see it in the test if something breaks or not. The producer, the signal, now also has to do something. Because once the signal function is called by the computed, it says, oh, I am the producer and I have been accessed. And there is a function which says producer accessed, and the signal itself registers or passes it on to it. And this producer accessed function is actually one which is quite large. It's also, I would say, one of the central functions that you have in the source code. What producer accessed is doing is that it says, okay, I'm being accessed as a signal. So first of all, I need to check if there is an active consumer. If there is, then I also need to check if I'm not already aware of that consumer. So I don't want to add in multiple times. So I have a if condition where I say, well, if an active consumer is set, and if my consumers do not contain the active consumer, then I'm free to add him or to add it to my consumers array. So then I say here push, and I say here active consumer. Okay. And this is done always when this function is called. Now the producer is aware of its computeds. And then it needs to update them. So we have here our update function. We have here two possibilities where the signal changes its value. That's the set and that's the update. So what I have to do here is that I have to say after I updated the internal value, I need to notify my consumers. So there is producer notify consumers, and I'm passing the node to it. And because I have missed that part in the rehearsal, I'm going to copy it right now, because otherwise the test will not work. So I'm adding it here as well. So set and update once the value has been set. That's important, not before. It needs to notify its consumers. Create function, yes, create place. And what we're doing here is that we say, okay, this is type T, and it's not very simple actually. We say node consumers, we iterate over them, and for every consumer, we just say we call the function notifying our consumer that we have been changed so that the consumer can now react on that event. And because theoretically, or not just theoretically, also in practice, the reactive node, I mean, you see already where that goes to. That's kind of a graph structure which will come out of it. It can also be the case that now this consumer is a producer again. So that means you have one computed which depends on another computed. So it would also be nice if this consumer is updating its own consumers as well. Sounds complicated. It's actually very easy to implement. We just need to say here, producer notify consumers, and we just take here the consumer, because now the consumer acts as a producer. Yeah, and you see I've saved the file and the tests are already green. So I actually wanted to make it a little more exciting. But yeah, this is it already. We have already now the solution for the reactivity, more or less. So again, what have we done? We have this active consumer. The producers need to be aware of them. The producers do that by calling, producer accessed. So the producer access means that the producer is checking if the active consumer is there. If it's there, it adds it to its internal consumers. And once the value changes, it updates automatically its consumers. On the consumer side, there are also two things to do. The consumer, first of all, needs to register in a way this on value change. So it needs to see kind of behavior, what should happen if it gets the notification. And we also have here the setting of the consumer. So the consumer before computation, where the consumer, or the computed in this case, sets itself as the active consumer. That's what we have to do. Then every time you see here something changes in one of the underlying producers, the consumers would be automatically triggered. Good. So, and now comes the fourth part, which is more or less about this glitch-free effect or the push-pull algorithm. How does that look like? We have again the same situation, a very similar situation that we had before, where we are counting the amount of times where this computed function is internally executed. In this case, what we actually want to do is that we want to avoid doing it unnecessary. So we have, for example, we say here in this computed, there is a heavy computation. So we don't want to run it if no one's really interested in it. We have here this total, this is the new one. And we say, I would expect if I access it, of course, for the very first time, then the computation needs to run, obviously. So we would expect here that it is 1 true. And now it's interesting, because now I say I'm updating it one time and then a second time. I'm updating the underlying signal. In our implementation, as soon as the underlying signal is updated, we know that the computation reruns. So we would end up here, or we actually end up now, with a computed count of a value of 3, not of 1, but we want to have 1. Because what we say here, this computed count is so heavy in terms of performance. If we don't want to access it, we don't want to run it. We have just updated the lunch, but nobody asked for the current value of the computed count. And then once we say total, then the computed count should be executed, but of course only once, because then it only takes into consideration the last value, which in this case is to 1. And this is a little bit problematic, because one time our computed should know about its producer, should be updated, and then there is a kind of a constraint where we say, well, my dear producer, I know that you want to update me, but I'm not interested because nobody accessed me already right now. It's a little bit of a tricky situation, but actually, surprisingly, very easy to fix. Where's the animation? There it is. Same situation that we had before. Caller, computed signal, active consumer, consumers. So the caller starts again by activating the computed, active consumer, and so on. We know already how it works. And then, or now, the signal gets an update. So signal has a new value. What the signal is doing now, it is still contacting its consumers, but it kind of marks the computed as, or it says to the computed, hey, look, I have a new value. I don't know about you. If somebody wants actually to have the value right now, I'm just telling you. So next time somebody wants to have the value from you, you would have to rerun your computation again. And this is what the computed is doing. The computed says, okay, I'm not going to rerun my computation internally. I'm remembering that my underlying signals have changed. So I'm waiting now for my caller or for the next time when I'm being activated. And only then do I run my computation. This is what's going to change now. Because now the caller comes along and says, okay, I want to have the value. Then the computed activates the signal, fetches the value, sets itself, and then the caller gets the right value back, as it was before. So the main difference is that we have still the notification in place, but the computed doesn't run the computation just because the signal was changed. It marks it internally, there was a change, but waits for a caller or that somebody accesses the value from it. So everything that we have to change now, and let me quickly now add here the test as well. So I think that's test number 5. Yes, there is now an amount for our lunch or for our meat. So I say here amount, that's an optional value. So what do we have to change? Well, we just have to make sure, I mean, we could even make it here with on value change, but let's do it like it is in the source code. There is a property which is called dirty, and that's a Boolean. So the reactive node knows if it's dirty or not. That's more or less all of it. And then when obviously my reactive node is created, I can say, well, dirty by default, it's more or less, it's not dirty by default. And then in my computed, this one also has to change here. So when the signal is now updated, it doesn't rerun the computation, it doesn't trigger the recomputation. What it does instead is that it's saying now dirty is true. Yeah. So before it was false, now it's true. Yeah. And for our computed, now also some things have to change because the on value change does not exist anymore. It's just create a reactive node with an unset. And what we have now, or maybe not with an unset, let's just say here dirty is false or dirty is true. And then we only need to check here in our computation, in our compute function, if we are dirty. And then we run it. And once we're done with it, we just clear ourselves. So we say here no to dirty is false. But now we have more or less fixed it. So now just because somebody is calling us, we are just setting here dirty to true, but we are still waiting that we ourselves are really called so that somebody wants to have the value from us. And only then do we start with the computation again. So if I save this now, there is a syntax error somewhere. It's right here. Yep, now the tests are working. Let me quickly try. So I say here to be 2. Yeah, it should be 1, as it actually should be. And the tests are fine. And this, what I have done here, let me quickly go back to the animation here. This is in a way this push-pull principle. So from the concept of the graph of the reactive nodes, it's always push. So the reactive nodes, they push themselves. They are updating, they're notifying themselves. But the real value is only activated or is only computed when the caller or the reactive context pulls it. So somebody needs to actively say, give me the value. That's the pull principle. And the combination with the combination of these two, we get this behavior that we see here. And this is then also true for the glitch-free effect. So if I have this glitch-free effect, which was actually one of the main reasons why Angular chose to go with signals and not with RxJS. In RxJS, you don't have it. You have the notification completely through to the subscribers. But here we say it depends, obviously, when the caller calls for the value, but there is a time period. In Angular, I will say about it later, but when the effect more or less runs, or when the template engine starts to work, then it more or less starts to create this kind of reactive context. In the end, it's more or less like calling, and it's doing this asynchronously. So we know that the signals, they can update themselves as often as they want, as long as it's done synchronously. because the effect or the really side effects like a rendering, they will only be executed against the final values that the reactive graph more or less have. It will not come up with intermediate states. This is more or less what RxJS is doing. It will only start to render the final state. And that's more or less than the glitch-freeness. All right, so I am now more or less done. I said before, there are some advanced concepts where I don't have so many slides, actually just bunch of very few of them, and I'm just going to explain them in theory. But from my perspective, this kind of push-pull pattern and the understanding how a signal or how a producer communicates with a consumer, this is the essence. That's the core part of the signals that we have to understand, because it's not the same as it is with RxJS. But with the understanding that we have right now, we could in a way also derive or have an understanding what an implementation for the advanced concepts would look like. So we have here, for example, the effect, to make it very short, what you have with an effect, you always have to come up with some kind of a trigger. You have to come up with a caller. Angular always, you see here always this kind of concept of the watch primitive. So in the end, somebody, and in Angular, it's the framework itself, somebody needs to say at a certain point in time, now I want to have the values. In the first version of the signals in Angular, it was Zone.js. So Zone.js said, okay, now I saw that there was a change. Let's check if the signals have also changed. And these days now, with the latest version, it comes in the form of a microtask. So as I said before, it's, to make it short, it's done asynchronously. So all the synchronous execution, all the synchronous updates of the signals run through, and only then with the final one starts the actual size effect or the computations. And in the end, the effect, you can see it here as it is shown here. The effect is in a way a computed that doesn't return a value, but it also needs to be triggered in a way. Good. Advanced concept. Those things that I've missed and that would really extend the code base that we have here. Dynamic dependencies. It could happen that we have a computed where multiple signals are included, but they depend on a condition. So I have a if condition, and when I go into the true clause, then signal A is activated and otherwise signal B. That means it could happen that the producers change because now the other condition is true, and then I don't need signal A anymore. I want to go to signal B. What's necessary here is that we have to extend our reactive node quite a bit. The consumers now also have to be aware of their producers. So there is a bidirectional relationship between them. And the kind of producer accessed is always executed. So every time this computation function runs, the producer access is activated. And what happens then is that the producer read-register themselves in the consumers, and at the very end, the consumer then has a way to detect which producers have not registered themselves anymore, and it drops them. And there's also some synchronization in place that the producers also have to be aware that the consumers do not exist anymore. But in the end, you do this with a bidirectional reactive. So the consumers also have to be aware of their producers. Value versioning, very important. This is the thing with the equal function. So by default, as Evgeny has pointed out, I've seen him before in the chat, the equal function has now also changed in Angular. So every time you have an object literal, there is an object is, which checks. So our updates, they have to be immutable. We can't, and only then do they trigger. And then it could be that you provide your own equals function. So it's now up to you to decide if a value is actually a new value, or if it is more or less, if it is the same. And in that case, we have another problem, because if I'm now a computed and I'm relying on another computed, and this other computed, it's telling me, yeah, there was a change, but I can't tell you if this is a change which is interesting to you, because it could be in the end, from a semantic perspective, the same value. But I can only tell you if I'm rerunning the computation. What happens then when the signal is more or less activated, or when the computed is activated, that I, as a computed, I go to my parent computed and I ask them to rerun their computation. And what they do is that they will obviously rerun it. Then they will compare the current version that they have with the new one. And if the customized equals function says, that's more or less the same value, there was no change, then they do not upgrade or increment their internal version. And then the consumer of this knows that it says, okay, I have already version 1. The guy just told me that he's still on version 1, so I don't need to run my computation anymore, and I'm not dirty anymore. I don't have to do anything. So this is the way how the value versioning works. Also, we need to add here a little bit more of code. And then last but not least, memory management. In signals, we differentiate between two types of consumers or reactive nodes. There are the so-called real-life consumer and the non-life consumer. And the way how it works, that everything which you run inside of an effect, and the effect then also executes, it's computed and all that stuff. So the complete reactive tree, which is activated by an effect, and the effect can also be from Angular, from the template engine itself. So when you have to compute it in a template, that's more or less the same. But what happens then is that the so-called reactive context is generated, where all the participants of this reactive tree or graph are more or less live. And once we are leaving this component, then there is a cleanup process where the effect, or where Angular makes sure that all the kind of participants are being unregistered and more or less go away, so that the garbage collector can come along and can more or less remove them. That's the normal way. And then there is also something else. As soon as you call a signal in TypeScript itself, so just call the function without an effect or without an computed, then you're outside of this reactive context. And then, if I'm not mistaken, the difference is that the producers are not aware of their consumers anymore. Because if they are, then the producers would have a reference to their consumers, and then the garbage collector could not collect the consumers anymore because they are still reachable via the consumers. If I'm not mistaken, this is something which I have to look up again, but just to give you an idea how it works. So there is a very smart memory management behind it as well. And that's it. That's the end of my talk. As I said before, if you're interested in this memory management, it will be included in the second part, which will be a video which will be published on my YouTube channel, or you also subscribe to our newsletter on Angular Architects. And by saying that, thanks for your participation, and I think we have now time for a Q&A.
Great session, Rina. Thanks.
Thank you.
Yeah, let's look into the questions. Whether
there are many questions.
Yeah.
Oh, everything okay.
Guess some discussions before in general. Give me a second.
Here, I mean, he can answer them, I think, better as I can.
Yeah, much appreciation for you, of course.
Thank you.
Yeah, I guess there was some issue posting a link in the chat.
Let's
reach out to us, and we will share it, maybe via Twitter or something like that. Yeah.
Schnitzel, holy cow, there are vegans around. Okay, yeah, good. Yes, it's a vegan schnitzel.
Yeah, some kudos directly from the Angular team. Matthew is here in the chat as well. So
Matthew, that's why I said if there are deep questions, maybe we add him directly to the chat and he can answer it.
Yeah, definitely, I'm sure.
I don't think that there are actually any questions, right?
Yeah, but in general, if you have some questions, just continue posting them into the chat, and we can even add this after my session, another Q&A for Rina's session as well. Yeah.
Right. Okay.
Great. So thanks, Rina.
It's your turn. Yeah, thanks.
Thanks a lot. Thanks a lot. Then let's switch the slide deck. Fine. Okay, my session now continues with, again, signals, but this time state management with Angular signals. So let's look into that, which options we have currently available or are close to have a new solution, new APIs that we can use. Signals and state management. We will look into the Signal API once again and discuss whether the Signal API provided by the Angular team is already something like a lightweight state management solution. Then we will explore the Signal state function. This is something that the NGRX team is currently working on, likely will be released with version 17, at least in a developer preview, and is part of the NGRX/Signals package, where also the Signal store will then be published soon. Then we will also look into the present state management solutions in the NGRX namespace, like the NGRX store, and how the store can help us dealing with signals. And finally, we will also discuss a short demo about the signal store itself. So it's basically, it can be used for local state management. And the big question always is, how can we differentiate local from global state management? Which parts of the state belong into which store solution then? And we'll explore this as well. So my name is Michael. I'm also one of the trainers and consultants in the Angular Architects Network. I help people and companies with their Angular implementations by doing trainings, consultancies, and code reviews. And once in a while, I'm always also talking at some conferences in autumn and in spring, and try to have some interesting talks there as well. Typically, I'm working most of the time in Germany, but I'm myself located in Austria, and also try to help each and every customer anywhere else that is interested in our trainings or consultancies. So you can follow me on Twitter if you like. Always a good way to get a quick gasp of what's new in the Angular framework, interesting discussions, interesting blog posts, and so on. So feel free to join me, to follow me, to follow Rina, of course, with NG News, as we already talked before, but also, of course, the Angular team and all the other great Angular experts that always deliver fabulous content. If you like, you can also book a workshop with us, and we will help you and your company to implement the Angular story right. So let's dig into the contents now. We will first start with the signals reactive primitive itself. So basically, the characteristics here are that the Angular team, as Rina already explained, was looking for an implementation that helps us to trigger the updating logic of the Angular application in a more fine-grained way. And there were some targets, or are some targets, that the Signal library could fulfill in a quite solid way. Solid way is basically, I said this for a reason, because solid.js actually had a big impact on the whole Signal story in the front end, but also Knockout, as it was previously discussed in the chat. So basically, this reactive primitive can always return a synchronous value. So in that case, similar to a behavior subject. It will not update if the same value is passed in. And in the newest versions, this also means object references and array references, which is, in my opinion, a quite important change for the framework to get the story right. And it can also update consuming logic. That means, as Rina explained you in detail how this works internally, this is the magic behind the Signal implementation, that we have really a kind of subscription management, but with fewer efforts, with almost no effort compared to RxJS. That doesn't mean in any way that RxJS is a bad implementation, but it means that the signals implementation can definitely help you in that area, reading a value, getting access to a value. Also, in some cases, if you like, you can receive updates. You're getting notified. The push concept where we can lean back, our source code can lean back and be sure that it will be updated, it will be notified if the signal changes. That's basically similar to RxJS, but the subscription management is far easier in that area. So let's come to the similarities and also to the connecting points between signals and RxJS. Basically, signals are no direct replacement for RxJS. This is important to understand because RxJS is a fabulous library that can fulfill different purposes for synchronous reactive behavior, for asynchronous reactive behavior, but also for really receiving all the necessary events that you're interested in. So one advantage of the Signal API of having this glitch-free behavior where we do not have states in between, this is kind of a good thing for rendering, but maybe it's not the best thing for logging, for example. So if you want to receive each and every event, signals are maybe not always the right API. So although signals will likely, and this was already mentioned as a target for the Angular team, not something that they will implement in the next major release, but something for the future that one day likely the Angular framework will declare RxJS as optional so that you can use it if you need it and where you need it, but you're not forced to. The same will also happen for Zone.js then. So basically it's a good situation that we, for simple applications, may not necessarily need to install RxJS. On the other hand, for a lot of Angular applications dealing with reactivity, and as we're working with the front end, reactivity is quite an important thing. I'm quite sure RxJS will still be relevant in future as well, but maybe not the only solution to write your Angular applications. So to sum it up, once again, subscription management is something that is getting easier here, and it's also easier to use signals in the template, read the value by just using a function call, and the same applies to RxJS, so no subscription necessary here. This happens behind the covers. So now the question, signals. Is the Signal API already some kind of state management? And I would say yes, because we have a writable signal here. The signal is a function and an object at the very same time. We can pass in an initial value, and this makes sure that we are always getting a type compliant value back at any point of time. But in certain situations, the value can also automatically update. When does this happen? For example, in the template. If we are using a signal read in the template, like here, I'm using my user signal that has an object passed in as initial value. This object has the property name, and my name is assigned currently. Then I can use the signal read it by just calling a function, and then this object is returned where we can then read the name property. So basically, as we use it that way in the template is already a reactive node. It's already a reactive consumer, and that means the template is automatically updated. The signal automatically notifies the so-called reactive LView consumer of the signal implementation, and that will lead in future at least to a change detection trigger, so that not only our component, but even smaller parts of the component, embedded views, one single line of a table that was rendered out with ng4, all of that can be updated without any burden by directly knowing where exactly the update needs to happen. And this exactly is based on Angular templates on embedded views. What else can we use with signals? Of course, besides reading, we can also write a value into that signal, back into that signal by using user.set. I can pass in, for example, Manfred's name into my user signal. So maybe I know Manfred's login data and can then log into a streaming platform where we do meetups like today. And we can also use the update method. This was also mentioned by by Rina before. The Angular team was discussing in the recent weeks whether the mutate function should really be supported for the Signal API that will leave developer preview now with Angular 17. So the first implementation that we know right now will likely leave the developer preview now with 17. And basically, it's a big decision whether to support mutable updates or to not support mutable updates. This was an API that was inside the Signal implementation from the very beginning on. So in February, as we first saw the first Angular team implementations on that, mutate was already present. But now they removed it. And I guess quite some people will be disappointed by that. But to be honest, I expected it from the very beginning on, or let's put it a little bit differently. I was very surprised and interested how the Angular team will solve the issues with not working with immutability, because this has definitely some consequences that we know from state management since decades, actually, that it's quite a good thing to work with immutability because it's more performant to track where the update actually happens. And I guess this might be the reason why they also went with that decision of first removing that API, making sure whether they can support this in future. But, as an API is introduced and production supported, so without developer preview, then it's hard to change that API in future. So maybe it was the better idea to first remove it and then maybe discuss whether there's a chance to put it back in future. We can also work with derived state, as you have seen in Rina's session as well. So with computed, and we can also use side effects. So all of that are our APIs that we are also using in state management solutions, creating derived state with selectors in NGRX, for example, creating side effects with the NGRX effect package to trigger some asynchronous logic, or in this case, we can log out something to the console. The Angular team already asked the community as well on Twitter, so what are the use cases for effects? Because to be honest, everyone would like to avoid a lot of effect implementations if they are not really necessary. But I guess they will be necessary, at least at the beginning, because there are some APIs that are currently framework APIs that are not supporting signals at the moment. So if you want to listen to a signal change, and based on that signal change, write something into an Angular form metadata object, this could be, for example, something that you implement with an effect. So it could be for at least some months a good solution to use effects to make sure that those APIs that are not already working with signals can be polyfilled with an effect, at least in between. Yeah. At the end, of course, it would be better to avoid effects if possible. So let's look into one implementation where we could refactor a current application into using signal state. This is one of the APIs that the NGRX team will offer soon. We already know parts of the implementation because Markus Stanimirovic, one of the NGRX team members who is really doing a lot of fabulous stuff with TypeScript, with NGRX, basically, he opened an RFC some months ago and already shared his basic first implementation with the community, which was really a nice way of introducing a new API. And basically, I copied over the last version of the signal store and signal state implementation of his playground application. There's already something available in the NGRX package. It's not 100% one-to-one the same, but quite similar. Some methods living in are not present in the playground application. Those are the other way around. So let's look into our demo application. I have our famous flight search engine here. So still, we can look up some flights and let's see whether it still works after my live coding. I'm curious as well. So we can look up some flights here from Paris to London, and basically the flights are shown with a card design here. I can select the flight, so the background color changes, and also that information of the child component is then visible here in the shopping cart in the basket object here. And we can also navigate to an editing view and so on. So let's stay here for a moment. If we describe that application, then we can figure out here is a filter area where we can put in some city names, Paris and London in my case here. And then I can hit the search button, a server call happens in the background and brings us back our flights. So if I initialize this view again, no flights at the beginning, then I look up my flights and they are shown down there. Currently, this application is implemented without signal usage here. So basically a simple smart component, it injects a feature. This injected feature is implemented with the NGRX store and effects package. That means I have a simple facade here. This is a pattern that Brandon Roberts once showed in one of his YouTube sessions. I really like that a lot. It shows you a simple NGRX implementation in one file. So basically some actions where we can trigger a flight load, an action to trigger a reducer afterwards to write data into our global state management. Then, of course, the state definition itself, how the state looks like, which types are currently supported in the global state management, which properties are defined for the initial state and so on. And then some simple reduce implementations, so how to write a new flight array into our global state management, the same for the tickets. And here, one nice API in the NGRX store package, create feature, where we can pass in reducer logic, and on the other hand, also selector logic. That means we can automatically access all those properties. So the selectors for the first level of the properties here are written for us automatically. They are available on the feature itself. And then we can reuse those selectors to write our more complex selectors. So in this case, I would like to show only the flights where my actively logged in user is booked to. So in this case, if we scroll a little bit higher, I have some flight IDs here that then match a certain flight that is then shown on the screen. Basically, the nice thing about this is it doesn't mean that you always need to write your global state management implementations into one file. But what I really like is using all those modern APIs, like creating an effect in a functional way, if you like. Still, classes are supported, but functional effects are possible as well right now. We can also use and provider function, so we can provide a feature state and some feature effects and return those from a provider function that we can use with standalone APIs in our router configuration. That means if you want to connect the store via lazy loading, then we can put them into the routing configuration here. So I provide my booking feature, I provide my router store connection, and all of that is then added to the application as soon as someone first navigates to the booking area. So this is lazy loaded in the top level routes here, if you look at that. So basically this store implementation here also at the end offers us a nice facade. So the facade pattern implemented in a few lines of code. So without a class in this case, just an object that is returned from a function. This is then checked function that I'm using in my component. It uses an internal dependency on the store. It returns an object with two observers and two methods to search and to save the results then. That's basically what we are now using in the component. So that's the reason why the component logic in this case is quite lean. Basically, we're just injecting our facade, and we care about some properties that are currently implemented without signals. That means from the to value for our two city names, an urgent flag and a basket object that can manage us different selection of the flights. If I turn to my template, we can see that we are using here template-driven forms, so ng model, to have a two-way binding to our properties here. And it could be our target right now to refactor this to a signal-based implementation. So refactor our current properties that are normal string and Boolean properties and object properties to a signal implementation. We can do so by switching back to this component TypeScript class. And first of all, I will add a type here. So type local state equals, and then I would like to define some properties. First of all, a filter, and the filter is already a type that is present here in my code base. So it's a flight filter. If I hover over that, or we look into the filter itself, it has a from value, a to value, and an urgent value, quite the same that we have available as properties in the component right now. And then I would also like to use a basket. And the basket has the same typing like down there. It's a record of number keys and Boolean values. So let's define this here as well. That's my local state. I can use this afterwards to create signal-based simple local state management. Why do I use protected here? Because we nowadays can use protected keyword here, access modifier, that we use those properties in the TypeScript class and in the template. So it's like with inheritance that protected is allowed to be used in the template then, in contrast to private. So in this case, I create my local state here. The local state has an assignment now, and it uses signal state from my signal state library. Just change the package name, give me a second. So I have a TypeScript package name for that at NGRX signal store. So it's not published yet, the package. So this namespace doesn't exist on NPM yet, but it's part of the repository copied over from Marko Stanimirovic Playground application. Okay, local state. And then I can define those properties that I would like to manage as signals right now. And it even supports nested signals. That means, first of all, to fulfill the type signature here, I would like to define a filter, and the filter has some values. And we can directly use those values from down there and copy them over here, remove the protected, of course. And that's basically already the start of our refactoring. Let's switch to some commas. And then I can also use my basket object. And the basket has also the same value then down there. And of course, I need to remove my equal signs and turn them into columns. Yeah, sometimes copying is more effort than writing it on your own. You'll know that. So let's do it that way. And now we have a type compliant signal state. That means each and every property here on first level, but also on lower levels, can be accessed as independent signals. That's quite nice. I also removed that protected, of course, and then we can try to refactor everything inside our template. So to make this really, the whole use case working again, because at the moment it would not work in our running application. So first of all, let's take the language service assistance here by having those underlined values here. We can use our local state dot filter dot from. And as from is a signal, I need to do a signal read here to really access my state. And I also remove the two-way binding here. So at the moment, by using that API, give me a second. From doesn't exist. Give me a moment. From should exist. Local state filter from. Give me a second. Local state filter from.
Michael, did you maybe call filter? That's the signal. Did you call filter and then from is just a property? I'm not sure. And then from is more as the
I guess it should be a nested signal as well, but you're right. you're right, it works right now. Yeah.
I mean, you can, if it's nested, you can still call the from, but the filter has to be called.
Yeah, I guess this was the error, right? No. Give me a moment. Just to make sure there's nothing wrong in my implementation here. Because I guess it should be a nested signal if I'm not wrong. So
maybe you also call local state. That local state is the signal.
Yeah. Just 1 second.
Yeah. Yeah, we have it in a minute. Michael is not just looking it up.
Yeah, let's fix this for a moment with the filter. Sorry for that, and I will do further explanation on this later on. So we can read the from signal here out of the state management, and basically, I guess it's really the reason it's that it returns the value for this level, but not for the next afterwards as well. Basically, the same can be done for the rest of the properties here, but there's definitely an issue in the other direction. So if we want to have two rebinding again, we also, of course, need to respect the update that comes with the event binding of engine model. So the input field is also returning us a change event, and the change event then also needs to be respected to be written back into the component later on. Yeah. So first of all, let's try to refactor this as well. So we can use engine model event binding, engine model change. And here we can write a method to update a specific from value, for example. Yeah, that means looking back into our class here, at the moment we want to change something in the local state. There could be a filter update method. And into the filter update method, we can pass in a partial state, for example, yeah, partial state for the filter. This doesn't return anything. And here I can show you how to work with this signal state interface right now. This dot local state dot. In this implementation, we still have the $sign update method. In the current namespace of Egger-Zikes, there's already a patch state value, as patch state method that we can use to update the signal state, but also the signal store. This is one of the previously mentioned differences between the current implementation in the Playground application and in the Egger-Zikes namespace. In the Egger-Zikes namespace, for example, at the moment, there's another interesting part missing, like the Rx method that I will show you afterwards. So how does this work? Quite similar like we used to work with the full Redux pattern. So in this case, we can return a state here, and this state then matches the state above here. So in this case, we can first of all read in everything that is currently written into the local state, and then we can update nested levels here. So in this case, we just read in states again with the spread operator state dot filter, and then we can also add our partial filter here afterwards. So no matter which properties come in via that method, we can write them now into that state management. Yeah, so it should then update the according properties there. We can use now that method in the template. So at the moment, this is really getting more. It's much more effort than we're used to work with without signals at the moment. But be sure that this will change. I will refer to that afterwards in the slides as well, because we will receive signal components with signal imports, and this does not only apply to to components APIs alone, but also to directives, of course. That means like ng model is one of the directives we're using here in the template-driven form integration. And as soon as this supports signal-based inputs like the so-called model input, where we have two-way bindings, then this story is getting much easier again. But for the moment, we can use our filter update method, and this filter update method can then receive a partial property of the flight filter, which in this case could be my $ event that I send up from a input field. Yeah, this would be one possible way to support a method that then can also be used with to and with urgent and so on. That means what I implemented right now here for the ng model in this place, we can also use that for the to ng model implementation, for the urgent. And it's also kind of tricky if we scroll down there. For example, for the basket object here, as we have seen previously with the typed state here, it's an object consisting of ID keys as numbers and values as Boolean values, and writing that back without signals it's quite easy. We just access the correct property out of the basket model object and then write back the Boolean value. With signals, again, this is getting a little bit harder, at least at the moment. Again, here, as soon as we have signal-based bindings, this story will likely get much easier again. So again, like for the flight filter implementation, we can use an own method, and this method can then just update one single basket ID. So let's implement this as well. For the basket update, basket ID update, this can then have the argument ID number and the Boolean value selected. This does not return anything. And then again, I can use a similar implementation like here. So I take the signal update method, pass in my state here, and then I write in a basket object here. I read in all the present properties from state.basket, and I can update a single ID by using the square brackets here. So I pass in my ID here, dynamically out of that variable, and then I pass in the selected. That's basically how we could provide an update method for that property binding as well. So let's save this. Let's return into the code here as well. So again, we need to split the two-way binding into parts. So the basket ID here comes now again out of the local state dot basket, and then here we have the IDs that we can read out. That's basically what shall be written into the input boxes, and the selected change. As we're using the two-way bindings and split them off, then we need to add the change for the event binding part. And here we can pass in or use our basket ID update method. I pass in my flight ID, and I pass in my selected state. Where does this come from? Again, from the $ event implementation. Fine. So basically, this was the first part to get signals into our application. As you have seen at the moment, the updating part, no matter if we're using the Signal API directly or if we're using the Signal State API from the Signal store, that also provides us nested signals, at least on that level here. It is basically helping us to turn the application into a mutable signal state management solution in a quite lean and straightforward way. But as you see, it has some rough edges. So at the moment, as long as the Angular framework does not fully support all the reactive bindings that were already announced to be implemented with Signal components, the story can be a little bit more complicated in some cases. Yeah? Let's also look into other parts of the Signal API. For that, I switch back to my slide deck. So basically, after the Signal state, it's also important, what do we do with present RxJS implementations and NGRX implementations? So I mean the full Redux pattern with the store and effects package. Which assistance do we get by the current framework APIs to have a good interoperability here as well? So first of all, we can use the toObservable method, which comes out of the core package and /RxJS interop. So with that API, with those functions that we simply can import, we can turn a signal into an observable stream. But be aware of one thing. It uses effects, so Signal Effects API behind the covers. And if your signal, and you know this is always the case, it returns synchronously a value. Unfortunately, the Angular team did not implement this here in the toObservable API. I hope they will change this in future, because at the moment we're using an effect implementation and we are returning the value of the observable then as asynchronous value. So it's not returned immediately by the observable stream, but with a slight asynchronous delay. To be honest, I'm not a big fan of that implementation. I guess they could have solved it differently by using the internal framework APIs. They presented some arguments why it is implemented that way, but I guess it would be a more solid approach, returning it synchronously by just comparing the value version. Actually would be an internal API of the Signal implementation that we could use here to really allow a synchronous return of the signal value. This would really be a great change, to be honest. On the other hand, we also have the opposite direction. So if we have an observable stream, we can return that observable stream, or we can convert that observable stream into a signal. What does this mean? Which consequences are connected with that? ToSignal automatically subscribes your observable stream. So at that time of definition, when we write our code with a property, for example, and assign ToSignal and pass in an observable stream, it means it immediately subscribes to that observable stream. It does not behave like a computed value that is only processed if there is a consumer. Actually, in this case, the subscription to the signal happens automatically at time of definition. So this is also something, I wouldn't say that this is something negative, but I would say this is something that we need to be aware of. We have this automated unsubscription management at the end of the component lifetime, but nevertheless, keep in mind, if this would be a timer, for example, the moment you define this, the subscription happens and the timer starts processing. To be honest, here as well, I would love to have a lazy API as a configuration option, at least, to turn this into a lazy subscription. That means just started subscription at the first signal read, but not initiation, at least, via opt-in configuration. Then we also have an API that is not directly connected to signals, but quite useful for observable streams, take until destroyed. We can inject that operator via dependency injection and then use it in our observable streams of the component. It would then mean that the component is automatically unsubscribing all those observable streams that use take until destroyed. So quite a pattern that we used quite for some time with take until, at least, but this time we do not need to manually create a behavior subject or a subject in general that can emit a value later on. It's basically easier to get the same result like we used the pattern in the past with take until. And now finally, the API for the NGRX global state management. So here we have the global store, and you actually have the store usage at the moment with this store.select, and then you pass in an NGRX selector function. In future, we can use, or not only in future, we can use it now. It's already available in version 16 for the full Redux pattern, the global state management, but also for the component store. We can use a select signal instead of the select method. So you just need to switch out the method call from select to select signal, and then selector function stays the same. So no need to update the selector function, but it then returns a signal and not an observable stream. So that's quite nice. This is something that we can also refactor in our code base. So basically, this is my global state management. And here I can change my observables here. Of course, in the facade here, we could also provide both. But in this case, I would like to refactor that to select signal for both selectors. And then we can update this in the search component as well. So in the template, we are currently using our observable stream here with the async pipe. And if you want to change this to a signal read, just remove the $ and the async pipe here and do a signal read like that. That's basically all. You can also see here is a for control flow syntax. So the new control flow syntax that was that will be introduced with version 17, but is already available in the current release candidate version, for example. We can use the new control flow syntax here. If you use Reactive 4, you also need to provide a track by information. So this was optional in the past, but is mandatory right now. This is good for performance reasons. And what's the reason for that? What does track by mean in detail? Why is it helpful for the framework to enhance the performance? Basically, just imagine we're doing a server call. And if we receive back a value of an array value of flights from the server, then it is automatically converted then into an JavaScript array, and therefore the array is created, the object references in the array are created, and that means each and every time we do a new server call, even if the server responds with the very same data, we have new array references and also new object references. And this is not that good not for ng4, but also not for the new control flow syntax, because by default it's comparing object references. So it tries to figure out, do I need to delete that embedded template first, so one row of a ng4 table, for example, or can I reuse it and just run change detection on it? So don't mix this up. Track by is not about just telling the framework, hey, keep that value as you have it and don't update that. It's just about remembering, is the current reference at index position 0, for example, is it the same like in the past, although the reference changed? And as soon as the framework figures this out, and we can help the framework by just saying, okay, don't compare the object references, compare the flight IDs. And if you find the very same flight ID, then you know you can keep that table row, but nevertheless, please run change detection, because maybe the flight ID 1 updated. There could be an updated in the city names, in the timestamp, wherever. Yeah. So basically, track by helps to keep templates that were produced by an ng4, for example, or here by the control flow 4 directive. And that's basically the Angular team went with that decision of making this mandatory to enhance performance and make sure that we do not delete embedded template, although they could be reused, because the data or the data structure is still the same, but we just need to run change detection over it. Fine. So basically, this was not tricky at all. So switching from observable stream to a signal read is quite easy cheesy. So basically, what else can we do? We can also talk about the new Signal Store API. And the new Signal Store API, first question is, why do we need to integrate this? Why should we integrate the Signal Store into our component? And basically, there are different reasons for local state management purpose, for example. I will show you some other use cases on the next slides as well. First of all, how can we create a Signal Store implementation? We can use we can create a new property or a new constant and assign, instead of the signal state that we used before, the Signal Store function to it. And then we can pass in different APIs. So if you look at that, it's quite similar to the provider functions that Angular offered with the standalone APIs. So where we can currently provide the router, for example, and then we add the component input binding feature. It's quite similarly implemented here. So we have the signal store, and then we can extend that signal store with custom behavior. First of all, we can define which state shall be managed inside that signal store. So in this case, with state defines, gives us the chance to define a generic interface here, or a type in this case, and provide in an initial state that that we do not have null pointer exceptions at the beginning. So same reason like for the full Redux pattern. And then we can use the method with signals and produce some nested signals. That means the selectors that we are used to work with in the full Redux pattern, the pendant to that, the equivalent here, is the with signals method, where we can really write our own logic on how to reuse present state signals and produce derived state with that. And then there are some other nice features like with methods, for example. So with methods, you can create update methods, for example. So similar to Redux reducers, we can also write asynchronous functions where we can pass in signals or observable streams, or just call the method with a concrete type, an object, a string, a number, whatever we need to pass in there. So it's quite nice on how to configure that signal store. And it's also quite nice on how to provide it. So basically, this constant here that is returned from this signal store call can then be directly provided as Angular provider. And it's up to you where you want to provide it. So if it is about local state management, likely it will provide it in a component providers decorator. If you want to use the signal store for global state management, then just provide it on root level. So that's also an option. Then accessing the store is just possible either via property injection with the inject function, or via constructor injection. That is still also an option. Fine. So what are the use cases? So when do I use the signal store? Is it only about local state management? Is it only about global state management? Are there some flavors in between? Let's discuss this as well. So the signal store usage, first of all, naturally, because it's quite similar, based on the basic concept, it's quite similar to the component store. Basically, first of all, most of the time people are thinking about local state management because we also have the Redux pattern as a global state management solution. So what is local state management? Maybe for one component only. There's one component, and this component needs to deal with complex state management, or at least not with easy cheesy state management with two properties, but with some kind of integrated state management in your code base. For that, you can register a local store on component level, and then also pass in, inject it into your very same component and work with that component. It is then automatically destroyed with the component. So as it is provided there, it also gets destroyed with that component. And we can use that pattern, local state management, actually, to reduce complexity. So what does that mean? We'll answer this in more detail in one of the following slides, but to put it in a nutshell, if you have reactive implementations, complex reactive implementations, if you have complex state management on the component level, if you implement all of that directly into the component, this is definitely possible, but it tends to be, you likely don't use the very same patterns all over again. And also, if you're looking at your developer teammates, likely everyone will use a little bit a different approach on how to re-implement the Redux, the reactive patterns actually. With the local state management API, it's quite similar to the full Redux pattern, to the global state management. This is an opinionated pattern. It means there are already some ideas and some concepts and patterns that we can reuse, and chances therefore are also higher that if you implement that in one component, later on in some other components as well, you will use quite similar patterns. So the code base is more aligned, and not only your own code that you have written, but also likely with your teammates, because everyone is using a quite similar idea of managing state and side effects. We can also use it as a global state management provider, as I mentioned before. This is then orientated on the app lifetime. That means until the next reload, or if someone actively destroys the app reference, as long as this does not happen, the singleton service stays available there. We can also use it as alternative for the Redux pattern, or maybe in future, let's see, maybe we get some APIs that we could even implement the Redux pattern with the signal store. At the moment, this is not possible yet. We can also use it for a group of components or features, for example. So if you have some smart components that could share a common logic for state management, for updating state that is relevant for those features, and this is not something that you want to put into the global state, then you can write your focused local state management solution, but this time for a group of smart components, for example. And it can also be used, and this is a quite nice use case, for a group of UI components. So if you have some generic UI components, those UI components, there's a parent and a child component that somehow need to interact with each other, then often a component state management solution for more than one component in a generic way is also something that is quite helpful, and you can use the signal store for that as well. All of that was what I explained right now also applies for the component store. I'm also curious how this will develop in future, because at the moment we have two solutions that somehow fulfill a similar purpose. Let's see how the story continues, I guess. Then the signal store will be the solution in the future if you opt in heavier signal usage, that you have even more deeply integrated signal support in the signal store implementation in comparison to the component store. So how does the API look like? Basically, love to compare this with the Redux pattern again, like the Redux pattern in a lightweight version. So basically, we can write an updater method with methods, for example, and we can pass in a value, an object, a string, a number, whatever we need to pass to that method. And then internally, it behaves, it has a similar implementation like a Redux reducer. You also saw this in my live coding previously with the update method for the signal state implementation. So you can maybe combine those two concepts of the global state management together into one concept. So with methods is something like that is directly callable, so without actions that you need to dispatch, like in the full Redux pattern. So it's somehow like actions and reducers combined, a method that I simply can call and pass in some values that are then added to the local state management. Selectors, the concept of selectors in the global state management Redux pattern. The pendant here, the equivalent here is with signals. That means this is the API to create your derived state. So custom signals, composition of signals, and so on. Can do this in the with signals implementation. And the effects are somehow a combination of with methods and the Rx method. The Rx method is currently an implementation that is at the moment not in the code base of the Nginx namespace. It's only in the code base of Marko Stanimirovic of the Playground application. But it's quite a magic or quite a powerful API, because this API allows you to write a method where you can pass in either a specific type, any type you can think of. It can be primitive value like a string or a Boolean or a number. It can also be an object. It can also be an array. But the nice thing about this is no matter how you type this Rx method, it can be the type itself. So you pass the type in, and then the method executes, it processes, and then it finishes and it's over until you call it another time. Or it can also be reactive. That means you can pass in a signal of that type or even an observable stream of that type. And then this method is called over and over again automatically as soon as the signal updates or the observable stream updates. And this is all of that is integrated into one API. So either the type or the signal of type or the observable of type. And that's quite nice, because this allows the usage of the method in different areas of your implementations, because likely if you call that method from the template, then you want to pass in directly the value and not something reactive. But if you use it in TypeScript class, maybe you want to pass in a reactive type like a signal or an observable to connect this once and receive updates each time the source emits a new value. That's quite powerful. So we can use it for both, to connect a view for processing and to also connect maybe global state management. That means on one hand, the template could pass in a value. On the other hand, we can also use the full Redux pattern with a selector and connect the global state management with that. This is also something that you can use this API for. So you can trigger state updates as well. So writing a new value into an update method. So one of those here that then update your local state. So some examples here, signal and observable API, automatically part of the type signature here, can pass in a signal or you can pass in a stream. This has automatic subscription management. That means you don't need to do an observable subscribe here. It happens automatically and it tidies up correctly if the instance is destroyed later on. We can also, as you can see here, this could be a signal reference that we pass in, but also an observable stream. And the same in a non-reactive way, so just calling the method once. The same method like above, trigger user update, can be just called by passing in a user, but you can also call an update method like add user directly and pass in a user object, and this is then added to the local state management. Fine, so let's look into the signal store as well. Give me a second. First of all, we can refactor this implementation here. Basically, we can get rid of the whole form and use a child component here, because I have a prepared app flight filter here. And this app flight filter, we can also use a self-closing tag today. We can pass in a filter object. And this filter object again comes out of our local state management, so via property binding. That means the filter object is available in the local state dot filter, and we pass this in our app flight filter component. So what I'm actually doing here, I'm replacing that filter UI with a child component actually, and this child component uses behind the covers signal store. That means it has a local state management inside. So we are not implementing the local state management here into the flight search component, but we have a flight filter component down there that already uses a local state management with the signal store. And like we have the filter here available, we can also react on updates that happen in that component by using an event binding that is called search trigger. That means the app flight filter component has a button inside, and let's leave this away for a moment. I just save this and then we can look into the UI on how it works. Let me quickly check whether there's an error in the template. I guess not. So now we have the filter component inside here. It still shows our initial values because, as you remember, this is something that we specified here in the local state management. The filter here is a signal, and I pass that filter down to the filter component, to the child component, or also can call this a UI component, a dump component. And this dump component has now kind of an extension here because this is a drop down. We can look up some flights. I have no search trigger, so the result is not showing right now. We will implement this. But then it adds the filter up there into a drop-down box, and you can switch to past filters afterwards. So each time I do a search here from Vienna to Berlin, for example, and hit the search button, this filter is added to the drop-down. So you can already imagine this is connected to local state management. So if we have two input fields and the urgent flag here, we somehow need to synchronize the from to and the urgent field here with the previous filter select box. So there's demand for a local state management to accomplish this. This is quite a nice use case because it perfectly shows where local state management can make sense, even for UI components that somehow need to deal with a little bit more complex state management. Yeah? It's not global state management because it doesn't matter if we navigate away and the previous filters are vanished. no worries here. But at the end, it enhances the user experience so that the user can switch to previous filters at least as long as he stays within that component. Yeah. So let's quickly update this as well. So the search trigger, and we can now say, please use our booking feature and the search method here. Search. And here I pass in my local filter again, so it has the same signature here. And now it works again. So we have from Paris to London our flights, and we can also enter any other Frankfurt to Vienna, maybe again. Look up some flights, and yeah, we have not implemented the filter update here. So something to add to our implementation right now. We react on the we passed in the filter to the child component. We also received the new filter value, but we do not write it back to the local state management. So if we switch this to the $sign event here, then the functionality in the UI should work actually. So Berlin to Vienna, those the flights, but to be fully honest, at the moment, we are not writing back the filter value to our local state management of this component. So we could update this by just using our filter update method here. So basically, let's implement a filter change method where we pass in our filter value. This doesn't return anything again, and then we are calling simply both methods. So the one that I just used in the template here. With the filter. And then as well, we are calling our own filter update method. Maybe we do this first. To have the local change first. Filter update, and again, we pass in our filter here. So what's left now is just replacing the method usage here in the template, and then it should already work. Let's save this. Let me quickly check whether it already is stable. Yeah, I have something left in the template. Give me a second to fix this. Local state management here. Basket that we show down there. And then it should be fine again. Okay, and now I can do my search. It's now also part of the state management of the smart component above. So Berlin to Vienna. Let's search this again. And basically it works. It can also recover my filters or rehydrate my filters from the previous searches. So Paris to London. So an enhanced user experience by just changing a UI component or the implementation of the UI component. Now the interesting part, how does all of this work inside the UI component? Because we just used it over there. Let's look into that. We can remove this. I have a flight filter component here with an input decorator and an output decorator. We used both of them. So as we have no signal inputs right now, I used a setter method here. Of course, this could also be implemented in another way with ng on changes at the moment or something like that. I just use the value that comes in and write this into my input filter form. So this is using reactive forms behind the covers. This is the reactive form for the group of input field and the checkbox actually. We write the value that comes in via input binding into our reactive form solution. On the other hand, we have an output trigger that can be triggered as soon as a meaningful result is available, and we want to send this back to the parent component. What else do we have? We have another state management, reactive state management, that is separated in the form control of the selected filter control, so our drop down that you have seen before. I'm using here typed forms, so the non-nullable option here as well. And then we just let us inject our local state management solution, so the flight filter store. The flight filter store is available here. So that's a separated class that resides here in the same folder as the component, because it somehow belongs to the component. It's only used here and not on any other level, so only for the local state management here. And here I have a local state definition. So I want to manage an array of filters. I would like to manage the filter of the current group of input fields. I also want to manage the current state of the selected drop-down box. And I would also like to provide an initial state here. And here you have the usage of those methods that we have seen on the slides before. So first of all, I define my initial state. I just create a constant here. So there's no class here inside. It's just a constant that has some nested features of the signal store. One feature is to specify the state here. So I provide a type information at the moment. As far as I know, it only works with types, not with TypeScript interfaces. So be aware of that, please. And we can pass in an initial state there. We have also with signals. So that's the way on how to create derived signals. So in this case, I created a derived signal that uses my filter array and returns the very last filter. So simply the last one that was added to state management. Yeah. Here I have a group of update methods. So I can update the filter array. I can update the input filter value. I can update the selected filter value. So all the logic on how we similar on how we use it in the full Redux pattern as well with reducers. So similar way on how to update the state immutably. We could also use similar patterns in future, like the entity package offers, to have easier update logic, maybe with less lines of code to write. And here down there, I use with method another time. I subdivided it into two sections. So the updaters first, and afterwards another call to with method with the effects. This has one benefit. I can directly access then the previously implemented methods, because this is chaining up all the dependencies. So in the next method, with methods called that I specify here, I can already access the update selected filter, the add filter, and so on. So I therefore put this into two different sections. That has also another benefit. You have clearly separated what's update logic and what's effect logic. I love to separate this. You're not forced to. You can also combine this into one method, but to be honest, I like to have it separated to have a clearer definition on where the update logic resides and where the side effects do reside. In my case, I have three side effects here. One side effect is just the search trigger to add the input filter to the input filter property here. Another one is to initialize the connection to the form state management. That means I want to pass in the value of my current input filter reactive form and also the select box, and write this to the local state management. And then I just simply use both of that in the all of those side effects in the component to basically connect the different reactive behavior over there. So I use the signal store, pass in the value changes observable of my reactive forms implementation for the input filter group, but also for the drop-down box. With that, it's directly connected. So as soon as the value changes in the reactive forms implementation, it also changes in the global state management. And the rest is then just using some side effects to react on them. That means I need to update the exactly opposite statement input solution here. That means if I enter a new value here, so again, I search from Paris to London maybe, and hit the search button, then as soon as I hit the search button, I would like to update the drop down above, and also the other way around. So as soon as I select a new value here, it should be written back to the input fields. So it's a little bit more complex than it looks at the beginning, but just looking into the UI here. So we need to connect different state management solutions the one of the reactive forms, the one of the local state management. And in addition, we also want to notify the parent component. And this is what happens down there. Here, I really select my latest filter that was added to the dropdown. And it's only added to the dropdown if I hit the search button. So as soon as the state management and the derived selector here changes, then the effect fires and reruns again. And then I use my latest filter only if it has a true C value, and I emit that value to the parent component. And be aware, it's really crucial. Manfred Steyer and Rina Hahnekamp and I were discussing this topic in the night session some weeks ago. It's really important that you put this into an untracked. If you forget about that, then it happens that your parent component search method that is triggered by the event binding is running in the reactive context of the child component. So basically, then somehow with a side effect that you typically don't want to have, because child and parent should be separated. Therefore, we're working with property and event bindings. Be aware of that. If you forget about the untrack, a side effect can happen that the method up in the parent component runs in the reactive context in the update cycle of that very effect. So be aware of that. If you use an event emitter, please remember the pattern to use untracked to not run into unintended side effects. That's the last learning for this live coding. I hope this was helpful to understand the full story. Of course, we can discuss this in a Q&A session afterwards as well. So let me quickly jump back to my slides to finish up. What is this all about? Why do we use a state management solution, global, local one? Both have in common. We have some complexity, we have some reactivity we want to deal with. So therefore, it's always helpful to have an opinionated API that you can orientate on, also your teammates can orientate on. And those clear APIs lead to clear patterns, and they lead to similar Redux implementations, or in this case, local state management implementations in this way, just a little bit more lightweight than the Redux pattern. It reduces overall complexity of your components. That means smart components really focus on that part that they are best in. They should provide a view model for your template. They should react on user interactions that is triggered. The user interaction is triggered in the template. Then it lands in the TypeScript class of your component, and then you typically forward it to other logical parts of your application. A local state management, a global state management, at injectable state service, whatever you like. But keep the component itself as dumb as possible. Dumb components, UI components should in any way not use dependency injection on feature-specific services. If it comes to smart components, you naturally are allowed to access feature-specific services. Nevertheless, try to avoid complex logic in your component classes, refactor them to a local state management solution, and that's then easier to extend and refactor your application later on. So the local state management shall process all the logical parts that a complex component implementation could do in its TypeScript class as well, but then likely that leads to quite big TypeScript classes that you normally do not want to maintain later on. So reactive and immutable state management is generally something that enhances your performance. That means immutability allows us to have a quite solid, and we already work with that since several years and decades actually. It's a way to track changes in an object or array structure quite easily without any burden of comparing single properties. And this is basically also important for the Signals API. So immutability is something that likely will also be used in future with the Signal APIs. Finally, signal-based components, what do we know about them for the future? The APIs are that the Angular team will likely provide as at least the things that we know based on the RFCs and some Twitter discussions. We will have a dynamic reactive input method. That means I could pass in a flight, and this flight is then a computed signal. That means if I pass in any value from the parent component via property binding to a reactive signal-based input, it will then be converted automatically to a computed signal. This has a huge benefit. You only have a dependency on that signal if you have a signal read then in the child component. If no one reads the incoming signal, then also no connection to your template, no update, and therefore also the change detection doesn't need to run. So that's quite important. The same for model. Model is just a proxy signal. So you pass in a signal from the two-way binding of your parent component. You receive a signal in your child component. Alex Ricabo told me on Twitter that it will likely be implemented with a proxy concept. So it's not the very same signal like in the parent component, but a signal that is somehow connected to the signal of your parent component. Yeah? And also the new control flow syntax has a big advantage for signal creation, because it will, as far as the RFC documents told us, it will convert the incoming data structures into signals. So we can also then rely on that the flight of the current iteration, the flight that is written from the iterable into the flight property here, will be of type signal. And this is also important then for the embedded views. That means your Angular application can then update on a fine-grained embedded view-based level. And this, of course, enhances your performance again. So quite more difficult in future to run into performance issues as soon as we have the whole signal story implemented, yeah, and available for consumption by the Angular community. So important for the future browser updates is that the signal-based change detection can then either work without Zone.js, or also combinations will be supported. That means your current code base that is relying on Zone.js, you cannot easily remove this without refactoring your whole code base. It will still work, but in addition, we can add signal-based components that could then work without Zone.js. And in a future version of your Angular application, if you completed your refactoring after the signal-based components were introduced, then the whole application could run without Zone.js. So basically, signals are then triggering the change detection, and they only process if there's a new event inside the signal trigger, actually inside the signal reference. Fine. So one final thing, just a quick demonstration. I published a library under the Angular Architects namespace to demonstrate a signal-based change detection. So basically, this is an application. We can reload this, and it's currently running with zone-based change detection. You can see here, make this a little bit bigger, how often the change detection actually triggers. It's a little bit unfair because, you know, change detection triggers duplicated in the dev mode, so it's a little bit less in the production mode. Nevertheless, you can look up some flights here, and you can see that change detection, the dirty checking, is going up. It shows some flights here. It can look into each part of the application. It demonstrates how often the dirty checking runs for specific parts. So we can also select a flight here, and you can see change detection goes up here, change detection goes up here. And basically, we can also then switch for the whole application, 31 change detection cycles here, for example. We can switch to the signals API here. So a demonstration of a signal-based change detection. I can do a search here as well. And as you can see, no update here because there was no change for the input arguments. Nevertheless, showing my flights down there. So as you can see, here was a second update, not only one. And then we can also type in some new information here. So instead of signal, maybe Vienna, and you can see for each typing the dirty checking runs because the signal is notifying the change detection. But still, only 5 updates here, only 2 updates on the top level. We can add an additional information. Flight is delayed, and you can see, although I'm typing here in this area, it only refreshes down there because the signal read only happens down there. It doesn't happen here while I'm typing because this is just user interaction. There's no need to update the UI. Nevertheless, it updates down there and shows that for each character that I enter, the change detection is triggered here, but not in the other areas of the application. So only 2 change detection cycles here, one here, one here. So it really demonstrates how the bright future of Angular will look like. It's of course not an implementation from the Angular team. It's just a slight modification of the core package that I did, but you can also see this based on this counter. Basically, it refreshes here without updating the rest of the application. So this is likely quite similar as it could be, at least on how it behaves in the user interface, as it could be with a signal-based change detection in future. So let's look forward to that, as we then likely will receive signal-based components with Angular 18 or 19, and then we can start implementing this for our applications as well. So I hope you had fun. Basically, that's all from my side. You can find 2 repositories on GitHub with, I will also commit the live coding with the Meetup signal state demonstration that I showed you, but also the signals experimental package with the signal-based change detection prototype. So I hope you enjoyed it. Yeah, let's look into the chat whether there are some questions.
Yeah, it was quite an extensive overview of the different state management possibilities we have. I don't know how you see it, Michael, but in my opinion, the way how the signals work, especially now with this kind of enforced immutability and the internal state management, as you said, it will just bring more people so that they can value the benefits of state management, because in the past this was always a big discussion.
Yeah. I guess there will be, as you have also seen in the live coding here, there are some things that are really rough edges at the moment. So things are getting easier because the framework will offer us quite easy options. So not any method that I needed to implement right now is necessary to be implemented in your code base. For example, yesterday, if you look on Twitter, Brett Billet showed us, Angular expert from Belgium, showed us a way on how to connect reactive signal-based form management with template-driven forms to a signal API. So this was also a great solution. You can look on Twitter and find his prototype for that. It's just a simple directive. So I guess there are a lot of different patterns will emerge on how to make the whole story easier, and a lot of nice APIs will be offered by the Angular team, of course, also by the NGRX team. So Marcus Stanimirovic, that I already mentioned several times, is doing a brilliant job. Also the rest of the team, like Brandon and Tim DeShriver and all the others, like Ryan and Alex Okrushko, they are all great developers. And I guess there will be some quite nice solutions in future for in the Angular framework, but also in the NGRX namespace. It will help us, actually.
Yeah. And how was it when you created this experimental signal component? How much work was necessary to pull that off? Because I imagine this is very hard.
Yeah, actually, I guess the use case is hard. It's if we go back to the running UI, it seems quite simple. But if you try to implement,
it always looks simple.
Fine.
It always looks simple. That's the point.
Yeah, it always looks simple. Yeah, for
Yes.
the user that is using the UI, it always looks simple. To be honest, I implemented this solution with the component store. Implemented it with the signal store now. I also, one of our workshop participants implemented this with RxJS. So basically, you have different prototypes on how to implement this. At the end, it's not getting any easier because the scenario is simply quite complex to connect those things together, to also make sure that if I enter a new value, the correct value is shown in the dropdown, that it also writes back the value to the parent component. So yeah, no matter which solution you use, it's quite a bit of effort to implement it.
Yeah. And I also meant the other thing that you have shown at the very end, where you have an application working without Zone.js. I mean,
I see.
That was really hard, I would say, even harder than this part.
Yeah. Basically, to be honest, it took some time. I don't know how many hours, to be honest. There are some iterations and a lot of dirty coding at the beginning directly in the core package. And of course, I needed to refactor this. But at the end, it's a simple hook that hooks into the core package, but I needed to modify the core package to make this happen. So you can try this out on your own. It's currently available not for the release candidate, but I will update this, of course, for Angular 17 as well. So it's currently working for one of the 16.1.7, I guess, is the version that I support right now. So nice to have a prototype. Of course, it's not meant for production usage, but the idea was that you have a prototype that you can work with and try out how signal change detection works and experiment a little bit, get a good feeling on how this works, and always provide feedback to me, always provide feedback to the Angular team, because then the story has less rough edges at the end, because community feedback is always welcomed.
Yeah, I think especially for somebody who is a library developer, that's really crucial what you have here, because I can already try it out how it would look like if my libraries actually would be ready for a zoneless world. And if not, I know already in advance that I maybe have to invest a little bit.
To be honest, it really helped me personally to fully, it's actually not fully, but to better understand the Signal API, because you're dealing with internals here and you ask yourself, why is this damn template now updating? And you try to change it a little bit and add some embedded views, some nested embedded views that are necessary here. Maybe you've seen this, there are quite some nested embedded views here, so that I can make sure that not the wrong parts are updated. This all will be easier as soon as we have the signal-based ng4, or the control flow-based the control flow-based 4, and also the signal inputs, because then the signal reads do not happen in the parent component anymore, but they only happen in the child component. That's a crucial update then.
Yeah. Okay, so about the questions. So first of all, of course, many congratulations here from Alain. Then also Angie Samurai was very happy about it. There was a little bit of a struggle in the chat between React versus Angular, and also
nice.
Hulk played a role in there as well. Yeah. So from Vladislav, if I read it correctly, Michael, I think you better read the Kyrillian letters.
My Russian skills. I'm really. I guess I need to rehearse to get this up and running again.
I think it's Vladislav, something like this. Yeah. I don't want to pronounce the last name. Right. There is just, I think, one main question: where can they get the source code? But I think you have shown this in the slides, right?
Yeah, I showed it on the slide. I will also tweet it, and we also will put it into the comments of the. On one hand of the tweets, but also in the comments of the meetup itself. So then you have everything connected, the slides and the GitHub repositories and so on.
Yeah. I see. Yeah, Mario was also very happy. So everybody's happy today. Yeah.
Thanks a lot.
Yeah, right.
So I guess no further questions in the chat, right? No further questions in the chat.
Everything what was in the chat I have posted more or less.
Super. Thanks a lot. Really enjoyed it, and congratulations to Rina once again, being at GDE right now, and she will of course update you as a community with the latest news in 100 seconds, right?
every week. Yeah, let's see if it happens next week as well, because I'm abroad, but I will try my best.
Great. Thanks a lot for your work.
Thanks. Okay,
fine, then we close this. Thanks for participating here, and I hope you all enjoyed it. Thanks a lot. Bye.
Thank you from my side as well. Goodbye.